Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, glad to be back and diving deep.
Yeah, excited to see where we land today. Always a fascinating journey.
Looking forward to it. Let's unpack some complex stuff.
So, to kick things off, I was reading this article about a new neuro-inspired AI model that's showing some pretty remarkable abilities in handling noisy data. It's using principles of neural oscillations and synaptic plasticity to filter out background noise, almost like the brain does, you know? It's not just about throwing more data at the problem. It's about making the model learn like a biological system.
That's really interesting, and it's kind of what I was hoping for. I have been following the trends in deep learning, and honestly, the improvements we've seen in recent years with larger models and more data are just astounding. Think about GPT-4, DALL-E, the progress in protein folding with AlphaFold, or even self-driving cars. These are all breakthroughs enabled by scaling up neural networks and having access to massive datasets. The ability of these models to generalize and perform tasks they weren't explicitly trained on is showing us we are on the right track. The way I see it, the path to AGI is not about reinventing the wheel, but it's about making those wheels much bigger and much faster, you know?
See, I am not so sure about that. I mean, the progress is undeniable, yes, but I think we're kind of hitting a wall with just brute forcing it with more data and bigger models. These deep learning models are really good at pattern recognition, but they often lack a deeper understanding, right? They can generate text that sounds very convincing, they can paint pretty pictures, and can drive a car in an environment they have been trained on. But when they encounter situations they have not seen before, they often just fall apart. They lack the ability to reason abstractly, to combine knowledge from different domains, or to really understand causal relationships. We need systems that can actually understand and reason. I think the future of AI lies in more symbolic approaches, combining the strengths of neural networks with explicit reasoning and knowledge. Representation, like graph databases with reasoning algorithms.
I agree with both of you, but I think we are missing a key element. Sure, deep learning is impressive, and symbolic approaches are vital. But what about spatiotemporal reasoning? The world we experience isn't just a collection of data points, it's a dynamic, continuous stream of information unfolding in space and time. Current AI models, even the most advanced deep learning systems, don't truly understand the spatiotemporal context of the world. They treat time as just another dimension, a sequential feature. But we humans have a rich sense of space and time, and that's crucial to our intelligence and how we learn and interact with the world. For instance, think about how we predict the trajectory of a ball, or how we understand an action sequence. We are constantly building internal models of our environment which are constantly updated with different spatial coordinate representations and their time derivatives. We need algorithms that are designed to operate directly in the space-time continuum and learn to translate from different coordinate systems. Right now, we're essentially feeding our AI flattened static images, when really it's constantly getting a rich, immersive, spatiotemporal movie.
That's such a great point about the spatiotemporal aspect. And it's really what the neuroscience angle highlights. The brain isn't just a static feed-forward network. It's got all these loops and feedback mechanisms and internal clocks. It's constantly predicting and correcting, and that happens in time. If we want to build truly intelligent systems, we need to be looking much more closely at those kinds of mechanisms. This article I was reading, which I mentioned at the start, was actually looking at using neural oscillations to process sequential data. The model basically learns to synchronize to the rhythm of the input, using time as a fundamental part of the information processing loop. It's not just treating time as a dimension, but as an actual processing parameter, almost like the way brain's neurons synchronize their firing. I mean, there are studies showing that oscillations in different frequencies are related to different cognitive processes, right? Like alpha waves are associated with attention, gamma waves with conscious perception. There seems to be an underlying mechanism linking time and information processing.
Absolutely, and I think that those biological insights can be useful, but I'm still very bullish on deep learning's potential. The scalability of deep learning allows us to capture incredibly intricate patterns. For example, think about how generative models like Stable Diffusion can create highly detailed and realistic images just from a textual prompt. It's a feat of complex pattern recognition, which would have been thought impossible just a few years ago. What is really happening is that through multiple layers and nonlinear activations, it's implicitly learned the statistical structure of the data. When you train these models with huge datasets, the parameters start to encode a kind of semantic knowledge in a way that we don't fully understand. The fact that these models have emerged that can perform so well on a range of tasks just by increasing size. I find this more compelling than thinking we have to fundamentally change the whole algorithmic structure. Yes, Maybe we can borrow some ideas from neuroscience, but the core of deep learning is so powerful in the way it can generalize from data, I don't think it is something to ignore so soon.
But that's the thing, isn't it? Implicit knowledge. These models are black boxes, even to the people who build them. It feels like we are just throwing things at the wall and seeing what sticks. The models don't understand why they get certain results. They can't generalize beyond the specific domains they were trained on. They struggle with common sense reasoning, right? Think about the common sense tests, where even very large language models struggle with simple physical principles or inferences. I am more inclined towards building systems that can explicitly represent knowledge and reason with it. We need to build symbolic representations that can link objects, relations, concepts, and actions. I envision models that can integrate data coming from neural networks with higher-level logical reasoning systems, building knowledge graphs that can be queried and manipulated. We can use neural networks to process raw data to extract the symbols, which will be passed to the reasoning engine, and then the results can be used to fine-tune the neural net. It's more of a hybrid approach, where each part of the system does what it does best. I think that's where true reasoning will emerge.
And I think this hybrid approach is key, but the hybrid needs to have an understanding of space and time. Just think, we don't interact with a database and then reason based on it. We are constantly immersed in our environment where our senses are interacting with the environment in space and time. Consider, for example, spatial navigation and how we use visual information to move around a place. How we build up a spatial model of the environment is not static. It's dynamic, and it's constantly updated with our changing point of view. A deep learning model might be able to recognize a building in an image, but it doesn't really know where it is in relation to other things and how this changes over time as we move about. This kind of continuous, dynamic spatial reasoning is missing from most current models. We need algorithms that can learn to build these kind of models, these dynamic spatiotemporal models, and represent the environment in different coordinate systems. The ability to transform from one coordinate system to another is at the heart of how we make predictions about our environment, and I don't think deep learning is well suited to this task. That's why I think we need something that's closer to how the brain represents space and time. Think about how the hippocampus creates these cognitive maps or how the basal ganglia is involved in sequential action control. All of these are dynamically evolving and transforming information over space and time. These neural circuits are not just static networks. They're constantly adapting to the inputs in the spatiotemporal continuum.
And there is something quite exciting in how different areas of the brain interact with each other to give this spatiotemporal reasoning, which I think we are missing at the moment. For example, the hippocampus is known to be involved with spatial mapping, but it does not do this alone. It interacts with other areas of the brain, such as the cortex and the cerebellum, to make sure that this spatial information is always accurate. And also in time. The cerebellum is often considered to be the part of the brain that is involved in timing and predictive control of actions. There are all these interesting interactions between these areas, and we can borrow those ideas and implement them in our AI algorithms. The models need to have dynamic architecture which can adapt to the type of information that's being processed in that moment. This means that the AI needs to have neural circuits that are interacting with each other and changing their communication depending on the information. Processing demands, like it happens in the brain. This type of dynamic computation requires more than just a feed-forward or even recurrent network. We need feedback loops, dynamic synaptic plasticity, and internal clocks.
I understand your points about the limitations of current deep learning, and yes, we do need to make progress in areas like generalization and interpretability. But let's not ignore the progress. For example, the recent advances in transformer models are quite amazing, not just in text, but also in other domains. They can learn incredibly long-range dependencies in data, a feature which was difficult for earlier neural networks. The attention mechanisms in transformers are implicitly learning relationships between elements that were far apart in the input sequence, without hard-coding rules. These models are learning to relate concepts and make logical inferences, not in a formal logical way, but in a way that is statistical. And they do it surprisingly well in many cases. Also, the ability for deep learning to learn from unstructured data is really important. Much of the world's information is unstructured. We don't have access to neat databases in real life. Our brains have evolved to learn from messy data, and I think deep learning, in a way, is starting to approach that.
But the fact that they learn these dependencies implicitly is kind of the problem, though, isn't it? It means the model doesn't actually understand why those relationships exist. They can only mimic them through statistical correlation. When you need a robust system that can make inferences in unknown scenarios, you need something more than that. You need the system to explicitly encode these relationships. The attention of transformer is still a black box when it comes to reasoning. It's like a very sophisticated curve-fitting approach. It does the job in many cases, but it's not the same as actual understanding. We need to move away from the idea that just because something is very complex, it equates to intelligence. Consider how we use common sense to interact with the world. For example, a toddler understands what happens if you drop a glass on the floor. This is based on an explicit understanding of physics, not just fitting parameters to a dataset. There is a very important qualitative difference. I think we need to explore the possibilities of knowledge graphs with embedded neural networks or symbolic systems that learn through reinforcement learning and are able to explore different hypotheses about the world, rather than relying on just passive learning.
And I think the key to that hypothesis exploration lies in the spatiotemporal nature of our world. The environment is constantly providing us with new sensory data, and we need to be able to represent the world from different points of view. We can't have a static representation of the world. It needs to be adaptable and able to incorporate new information as we explore. I'm thinking about how we process visual information, for example, how we are able to predict what an object looks like from a different angle. We build mental models which allow us to do that and to predict what will happen in our surroundings. Current AI models are not doing that. They're static models. They can only process data from a fixed perspective. I think we need to build algorithms that can actively transform the sensory information to different coordinate systems and predict the consequences of actions. Like our internal model of the world. There are models coming out now that are trying to take a 3D scene, apply transformations to them, and then use those transformations to predict the future state of the scene. It's those types of models that we need to focus on.
That idea of prediction is so crucial, and it really links in with the neuroscience. The brain is fundamentally a predictive machine. It's always generating models of what's about to happen and updating these models based on new data. It's not passively reacting to stimuli, but constantly trying to anticipate what's coming next. And this predictive ability is linked to temporal dynamics and synaptic plasticity. This means, if the brain is constantly adapting its internal model by changing the synaptic weights based on prediction error, then shouldn't our artificial systems be doing the same? We need to build AI that doesn't just learn from data, but actively learns to predict the future based on its internal model. And I think the key to achieve that is to try to mirror the way the brain implements this through oscillations, time-based neural processing, and dynamic circuits.
I agree that prediction is essential, and deep learning is surprisingly good at it. Just think about time series prediction, forecasting stock markets, weather patterns, or even the next word in a sequence. These models are able to capture dependencies that are happening over time and make accurate predictions. And this is all through deep networks learning to model temporal patterns. The recent work on video prediction is also very impressive, where you can input a few frames and the model can predict what happens next. The ability to predict is very much tied to the ability to capture the statistical patterns of the data. And in deep learning, we are getting good at that. And I do agree that neuroscience is really important and we can take inspiration from it. I think we should integrate the brain's processing abilities with deep learning to see what happens. It's not either-or situation. For example, the attention mechanism in transformers can be thought of as a kind of neural attention process, in the sense that is selecting information from the input that is most salient. And this mechanism does seem to mimic what is happening in the brain. We don't need to completely throw away all that has been done in deep learning.
But it is still mimicry, not actual understanding. It's not learning the underlying generative process. I am not saying we should throw it all away, but we must be very careful about what we think deep learning is actually doing. It can be used as a tool, but it's not the silver bullet to solve the problem of AGI. Take, for example, language. Language is not just a statistical pattern of symbols. Language is based on the understanding of the world. To really understand the meaning of sentences, you need to understand the underlying concepts and the relationships between those concepts. I think we need to move away from models that are just pattern matching and focus on those that are able to represent knowledge and reason about it explicitly. The idea of having a neural network to understand the low-level data and symbolic systems doing the reasoning is still my preferred approach. The current approaches are too focused on correlation rather than causation.
Yes, and the concept of causation is linked to the idea of building a model of the world that allows for active experimentation. This is missing from current AI. It needs to be able to explore its environment, try out things, and see how the world reacts. And it can only do that if the model is spatiotemporally aware. I also think we need to stop treating the inputs as just a set of data points. Current AI ignores that data arrives in a specific point in time and comes from a particular point in space. We need algorithms that are able to represent the world from different points of view and that can transform information across those points of views. For example, if we imagine an object in front of us and then move to our left, we can predict how this object will look. We constantly manipulate the 3D world using mental transformations, and we need models that can do the same. I think this is a missing piece of the puzzle, and that is the spatiotemporal representation of the world.
And I think the way we approach this, as we mentioned, should take into consideration the biological mechanisms that allow us to do this. If the brain can do it, we should be able to make a system that can do it too. If the brain can understand the world in spatiotemporal terms, it is because it has found a way to do that using its underlying biological hardware. We should use the same ideas to build our AI systems. For example, we should be looking at how oscillations are used for temporal encoding, or how the plasticity rules allow us to learn new concepts, or how different brain areas collaborate to build internal models. All of these are really important aspects for an intelligent system, and something that current AI lacks. I think that it is time to start moving away from a black box approach where we just try to optimize a model and try to build AI systems from first principles that are based on neuroscience. We need to build systems that are interpretable and that can be debugged. To me, that is the main research direction we should be focusing on.
I think that is a very important point. We need to move away from the black box models, and we can make them more interpretable. The research in using attention as a way to understand what the network is looking at is gaining momentum, which is great. Also, there are methods that are trying to visualize the activity of different neurons in the network and understand what they encode. And also, we need to understand the generalization abilities of the models to see what are the limitations of these approaches. All of this is leading to more robust AI systems that are less like a black box and more transparent, which is important. But in terms of future research, I am still focused on the power of scaling deep learning with new architectures that are based on the insights of neuroscience. I would like to see new models that incorporate some of the neuroscientific understanding of how the brain processes information. But I am still confident that with enough data and computational power, deep learning can achieve AGI. It's not a matter of completely throwing everything away, but building on that to go further. And I also think that we need better data sets that capture the complexity of the real world and avoid the biases that current data sets have.
Well, I do think we need to move away from black box models and focus more on interpretable models based on symbolic AI. The next steps of research I see are to find ways to combine the power of neural networks with logical and symbolic reasoning in a more principled way. We can use neural networks as preprocessors to extract the symbolic representations from raw data. But then, we need a reasoning engine that can use this information to make inferences and learn new concepts. The system should be able to reason about the environment and build knowledge graphs that encode relationships. I also think we should explore reinforcement learning approaches that allow the AI to actively explore its environment and learn through interactions. The system should be able to form hypotheses and then test those hypotheses, learning from success and failure. It's this kind of active learning process that I think we should focus on. My fear is that current deep learning will eventually reach its ceiling. It will become very efficient in recognizing known things, but it won't truly understand them. And we need true understanding to have AGI.
And I agree with the symbolic approach to an extent, but these representations need to be embedded in a spatiotemporal framework. My main focus for the future research is to explore algorithms that can learn to represent the world in dynamic spatial and temporal dimensions, that can transform this information from one coordinate system to another. We need to move beyond models that operate on static data points, to models that can understand sequences and change of perspective and are grounded in the spatiotemporal reality. For example, we can think of a new type of neural network which is directly operating in the continuous space and time. Current neural networks operate in discrete steps, and the information is transformed in a static manner. But maybe a neural network that works using spatial transforms can be the key. I would like to see models that are learning these spatial transforms and can actively navigate the world by constructing and updating internal dynamic maps of their surroundings. And I also think we need to move away from the idea that data comes from an external world and focus more on internal models that are constantly updated and are actively tested with data from the environment. It is not a passive learning process, but an active construction of a dynamic internal representation of the space-time continuum.
Well, this has been a fascinating deep dive into the different aspects of intelligence and how we should approach AGI. We definitely need to combine ideas from neuroscience, symbolic AI, and deep learning, as no one single method will solve the whole thing. I think we should keep exploring different ideas and push the boundaries of AI. So many things to research and to discover. Thanks for being here.
Absolutely. This was a great discussion. It always challenges my way of thinking, and I'm constantly learning new things. Thanks for having me.
Likewise. Always a pleasure to explore these topics with such different perspectives. It makes me rethink some of my assumptions too.
It was fascinating. I enjoyed listening to all your different opinions. It's clear that there are many different ways to think about intelligence. We need to work together to advance these ideas and push the boundaries.